To calculate the minimum demand for a feeder supplying 3 fixed space heaters, where one is rated at 19.2 kilovolt-amperes and the other 2 are each rated at 1 kilovolt-ampere, all operating at 240 volts single phase, you need to follow a few steps. Firstly, you'll need to convert the kilovolt-amperes ratings of the heaters to kilowatts. To do this, you'll multiply each kilovolt-ampere value by an assumed power factor. In this example, we'll assume a power factor of 0.8. For the 19.2 kilovolt-amperes heater, the calculation is 19.2 kilovolt-amperes times 0.8, which equals 15.36 kilowatts. For the 1 kilowatt heaters, the calculation is 1 kilowatt times 0.8, which equals 0.8 kilowatts each. Secondly, calculate the total load. This involves adding up the kilowatt values of all the heaters. So, the total load is 15.36 kilowatts plus 0.8 kilowatts plus 0.8 kilowatts, which equals 17 kilowatts. Thirdly, calculate the minimum demand. The minimum demand represents the lowest amount of power that the feeder is expected to supply. For a single-phase feeder, it is common to assume a demand factor of 75% of the total load. This accounts for the fact that the heaters might not always be operating at their maximum capacity simultaneously. Therefore, the minimum demand is calculated by multiplying the total load by the demand factor. In this case, it's 17 kilowatts times 0.75, which equals 12.75 kilowatts. Therefore, the minimum demand for the feeder is 12.75 kilowatts. It's crucial to understand the underlying principles that govern electrical load calculations, which form the foundation for safe and efficient electrical system design. Let's consider the practical context of this scenario. Imagine a workshop or a commercial space where these space heaters are essential for maintaining a comfortable working environment during colder months. The heaters are not simply added haphazardly to the electrical system. Instead, a careful assessment is done to ensure that the existing electrical infrastructure can safely and reliably support the additional load. The first step in this assessment involves understanding the power requirements of each space heater. Space heaters are typically rated in terms of their power consumption, expressed in watts or kilowatts. This rating indicates the amount of electrical energy the heater consumes per unit of time when operating at its full capacity. In this particular case, we have 3 space heaters with different power ratings. One heater has a rating of 19.2 kilovolt-amperes, while the other 2 each have a rating of 1 kilovolt-ampere. The rating of 19.2 kilovolt-amperes is expressed in terms of apparent power, which is the product of the voltage and current in an alternating current circuit. However, apparent power is not always the same as the actual power consumed by the load. The actual power consumed is referred to as real power and is measured in watts or kilowatts. The relationship between apparent power and real power is defined by the power factor, which is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all the apparent power is being converted into real power, while a power factor of less than 1 indicates that some of the apparent power is being wasted. In the context of space heaters, the power factor is typically close to 1, but it can vary depending on the design and construction of the heater. For the purposes of this calculation, we have assumed a power factor of 0.8. This is a reasonable assumption for many types of electrical loads, but it's always a good idea to verify the power factor of the specific space heaters being used. Once we have the power ratings of all the space heaters in kilowatts, we can calculate the total load in the feeder. The total load is simply the sum of the power ratings of all the individual loads connected to the feeder. In this case, the total load is 17 kilowatts, as calculated earlier. However, the total load is not necessarily the same as the minimum demand in the feeder. The minimum demand is the lowest amount of power that the feeder is expected to supply over a given period of time. In other words, it represents the sustained load in the feeder. The minimum demand is typically less than the total load because not all the loads are likely to be operating at the full capacity simultaneously. For example, the space heaters might cycle on and off as needed to maintain a desired temperature. The ratio of the minimum demand to the total load is known as the demand factor. The demand factor is a statistical measure that takes into account the diversity of the loads connected to the feeder. The demand factor can vary depending on the type of loads, the number of loads, and the operating characteristics of the loads. For a single-phase feeder supplying a group of space heaters, it is common to assume a demand factor of 75%. This means that the minimum demand is expected to be 75% of the total load. In this case, the minimum demand is 12.75 kilowatts, as calculated earlier. It is important to note that the minimum demand is not necessarily the same as the actual load on the feeder at any given moment. The actual load can fluctuate depending on the operating conditions of the space heaters. However, the minimum demand provides a reasonable estimate of the sustained load on the feeder, which is useful for sizing the feeder conductors and protective devices. In addition to calculating the minimum demand, it's also important to consider the voltage drop on the feeder. Voltage drop is the reduction in voltage that occurs as electrical current flows through the feeder conductors. Voltage drop can be caused by the resistance of the conductors and the impedance of the loads connected to the feeder. Excessive voltage drop can cause problems with the performance of the space heaters, such as reduced heating output. The amount of voltage drop on a feeder depends on several factors, including the length of the feeder, the size of the conductors, the current flowing through the conductors, and the power factor of the loads. To minimize voltage drop, it's important to select conductors that are large enough to carry the expected current without excessive voltage drop. The National Electrical Code, or NEC, provides guidelines for sizing conductors to limit voltage drop. These guidelines are based on the type of loads being served and the length of the feeder. In addition to voltage drop, it's also important to consider the ampacity of the feeder conductors. Ampacity is the maximum amount of current that a conductor can carry safely without overheating. The ampacity of a conductor depends on several factors, including the size of the conductor, the type of insulation, and the ambient temperature. The NEC provides tables that list the ampacity of different types of conductors under various conditions. When selecting conductors for a feeder, it's important to choose conductors that have an ampacity that is equal to or greater than the calculated load current. This will ensure that the conductors can carry the expected current without overheating and causing a fire hazard. In addition to sizing the feeder conductors, it's also important to select appropriate protective devices for the feeder. Protective devices, such as circuit breakers and fuses, are designed to protect the feeder conductors from overcurrent conditions such as short circuits and overloads. When an overcurrent condition occurs, the protective device will trip or blow, interrupting the flow of current and preventing damage to the conductors. The size of the protective device should be selected based on the ampacity of the feeder conductors. The NEC provides guidelines for selecting the appropriate size of protective devices. When selecting protective devices, it's important to choose devices that are properly rated for the voltage and current of the feeder. It's also important to choose devices that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, or UL. In summary, calculating the minimum demand for a feeder supplying multiple space heaters involves several steps, including converting kilovolt-amperes to kilowatts, calculating the total load, and applying a demand factor. It's also important to consider voltage drop, ampacity, and protective devices when designing an electrical system to supply space heaters. By following these guidelines, you can ensure that the electrical system is safe, reliable, and efficient. Now, let's consider a practical example to further illustrate the concepts discussed above. Suppose we have a small commercial building with 3 electric space heaters. One heater is rated at 5 kilowatts, another is rated at 3 kilowatts, and the third is rated at 2 kilowatts. All 3 heaters are connected to a single-phase 240 volts feeder. To calculate the minimum demand for the feeder, we first need to determine the total load. The total load is simply the sum of the power ratings of the 3 heaters, which is 5 kilowatts plus 3 kilowatts plus 2 kilowatts, which equals 10 kilowatts. Next, we need to apply a demand factor to account for the fact that the heaters may not all be operating at their full capacity simultaneously. For this example, let's assume a demand factor of 80%. This means that the minimum demand is expected to be 80% of the total load. To calculate the minimum demand, we multiply the total load by the demand factor, which is 10 kilowatts times 0.80, which equals 8 kilowatts. Therefore, the minimum demand for the feeder is 8 kilowatts. Now that we have the minimum demand, we can use this information to size the feeder conductors and protective devices. To size the feeder conductors, we need to determine the current that the feeder will be required to carry. To calculate the current, we can use the following formula: current equals power divided by voltage. In this case, the power is 8 kilowatts, which is equal to 8,000 watts, and the voltage is 240 volts. Therefore, the current is 8,000 watts divided by 240 volts, which equals approximately 33.3 amps. Now that we know the current, we can refer to the NEC to determine the appropriate size of conductors to use for the feeder. According to NEC Table 310.15b16, for a single-phase 240 volts feeder carrying 33.3 amps, we would need to use at least number 10 American wire gauge copper conductors with type TW insulation. However, it's always a good idea to use larger conductors than the minimum required to account for voltage drop and future load growth. In this case, we might consider using number 8 American wire gauge copper conductors, which have an ampacity of 40 amps. To size the protective devices for the feeder, we need to select a circuit breaker or fuse that is rated to protect the conductors from overcurrent conditions. According to NEC section 240.4d, the overcurrent protection for number 8 American wire gauge copper conductors is typically 40 amps. Therefore, we would need to use a 40 amp circuit breaker or fuse to protect the feeder conductors. In addition to sizing the conductors and protective devices, it's also important to consider the grounding and bonding requirements for the electrical system. Grounding and bonding are essential for protecting people and equipment from electrical shock hazards. The NEC provides detailed requirements for grounding and bonding electrical systems. In general, the grounding system should be designed to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protective devices will trip quickly in the event of a fault, minimizing the risk of electrical shock. Bonding is the process of connecting all metal parts of the electrical system together to create a common electrical potential. This helps to prevent voltage differences between different metal parts, which can create a shock hazard. By following the NEC requirements for grounding and bonding, you can help to ensure that the electrical system is safe and reliable. In conclusion, calculating the minimum demand for a feeder supplying multiple electric space heaters involves several steps, including determining the total load, applying a demand factor, and sizing the conductors and protective devices. It's also important to consider grounding and bonding requirements to ensure the safety of the electrical system. By following these guidelines, you can design an electrical system that is safe, reliable, and efficient for supplying electric space heaters. Always consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and regulations. Now, let's explore some additional factors that can influence the minimum demand calculation and the overall design of the electrical system for space heaters. One important factor is the type of space heaters being used. There are several different types of electric space heaters, each with its own unique characteristics. Some common types of electric space heaters include resistance heaters, convection heaters, radiant heaters, and fan-forced heaters. Resistance heaters are the most common type of electric space heater. They work by passing electric current through a resistive element, which heats up and radiates heat into the surrounding air. Resistance heaters are relatively inexpensive and simple to operate, but they can be less energy efficient than other types of heaters. Convection heaters work by circulating warm air throughout the room. They typically have a heating element at the bottom of the unit which heats the air. The warm air rises, creating a convection current that distributes the heat throughout the room. Convection heaters are generally more energy efficient than resistance heaters, but they can take longer to heat up a room. Radiant heaters work by emitting infrared radiation, which heats objects and people directly. They do not heat the air in the room, which makes them more energy efficient than other types of heaters in certain situations. Radiant heaters are often used in outdoor settings, such as patios and decks. Fan-forced heaters use a fan to circulate warm air throughout the room. They are similar to convection heaters, but the fan helps to distribute the heat more quickly and evenly. Fan-forced heaters are often used in larger rooms or areas where quick heating is desired. The type of space heaters being used can affect the minimum demand calculation in several ways. Firstly, different types of heaters have different power ratings. For example, a resistance heater might have a power rating of 1500 watts, while a convection heater might have a power rating of 1000 watts. Secondly, different types of heaters have different duty cycles. The duty cycle is the percentage of time that the heater is actually operating. For example, a resistance heater might have a duty cycle of 100%, meaning that it is always operating at its full power rating. A convection heater, on the other hand, might have a duty cycle of 50%, meaning that it only operates at its full power rating for half of the time. The duty cycle can affect the minimum demand calculation because it determines the average power consumption of the heater. Finally, different types of heaters have different power factors. As mentioned earlier, the power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all the apparent power is being converted into real power, while a power factor of less than 1 indicates that some of the apparent power is being wasted. The power factor can affect the minimum demand calculation because it determines the amount of current that the heater draws from the electrical system. Another factor that can influence the minimum demand calculation is the thermostat setting. The thermostat setting determines the desired temperature in the room. When the thermostat is set to a higher temperature, the space heaters will operate more frequently and for longer periods of time. This will increase the total load in the electrical system and the minimum demand. Conversely, when the thermostat is set to a lower temperature, the space heaters will operate less frequently and for shorter periods of time. This will decrease the total load in the electrical system and the minimum demand. The thermostat setting can also affect the diversity of the load. Diversity refers to the extent to which the loads on the electrical system operate independently of each other. When the thermostat settings are all set to the same temperature, the space heaters will tend to operate in unison. This will decrease the diversity of the load and increase the minimum demand. On the other hand, when the thermostat settings are set to different temperatures, the space heaters will tend to operate independently of each other. This will increase the diversity of the load and decrease the minimum demand. The location of the space heaters can also influence the minimum demand calculation. Space heaters that are located in different rooms or areas will tend to operate independently of each other. This will increase the diversity of the load and decrease the minimum demand. On the other hand, space heaters that are located in the same room or area will tend to operate in unison. This will decrease the diversity of the load and increase the minimum demand. The insulation of the building can also affect the minimum demand calculation. Buildings with good insulation will require less heat to maintain a desired temperature. This will decrease the total load in the electrical system and the minimum demand. Conversely, buildings with poor insulation will require more heat to maintain a desired temperature. This will increase the total load in the electrical system and the minimum demand. The weather conditions can also affect the minimum demand calculation. During colder weather, the space heaters will operate more frequently and for longer periods of time. This will increase the total load in the electrical system and the minimum demand. Conversely, during warmer weather, the space heaters will operate less frequently and for shorter periods of time. This will decrease the total load in the electrical system and the minimum demand. Finally, the occupancy of the building can also affect the minimum demand calculation. Buildings that are occupied during the day will typically require more heat than buildings that are unoccupied during the day. This will increase the total load in the electrical system and the minimum demand. Conversely, buildings that are unoccupied during the day will typically require less heat than buildings that are occupied during the day. This will decrease the total load in the electrical system and the minimum demand. In conclusion, calculating the minimum demand for a feeder supplying multiple electric space heaters is a complex process that requires careful consideration of several factors. These factors include the type of space heaters, the thermostat settings, the location of the space heaters, the insulation of the building, the weather conditions, and the occupancy of the building. By taking all of these factors into account, you can design an electrical system that is safe, reliable, and efficient for supplying electric space heaters. Remember to consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and regulations.